In this video, let's have a look at the integral from 0 all the way up to positive infinity, this improper integral, because the upper bound is not finite, of dx over 1 plus x squared times 1 plus x to the power of alpha. And in the end, we will find out that the integral value has nothing to do with the value of alpha. And the lemma for the method, I'm going to use two different methods. So I'm going to later use this lemma for method 2. But first, let's look at method 1. So first method. So the usual common technique to deal with improper integrals like this is that we want to, first of all, split it into two different integrals. So first of all, it's from 0 all the way up to 1. Then from 1 all the way up to positive infinity. Maybe let's just call the first integral I1, second integral I2. Now, I want to look at the integral I2. Integral I2. If I just let, the reason we want to later, we'll see the benefit of doing this. So for integral I2, we can just simply use the reciprocal substitution. We can let x equal to 1 over t. Right, so that way dx is just simply minus t to the power of negative 2 dt. Right? So also remember to change the boundaries. So remember when x is equal to, for I2, when x is equal to 1, t is equal to, also equal to 1. When x is approaching positive infinity, t is approaching 0. Right? Approaching 0. Here, t does not equal to 0, but t could approach 0. So again, we change the boundaries. Then what's inside the integrand? This time, what's the integrand? Right? First of all, dx becomes minus t to the power of minus 2 dt. Right? So we have a minus out here. T to the power of minus 2 dt on the top. What's the bottom? 1 plus x squared becomes 1 plus 1 over t squared. Right? Common denominator, t squared. We have t squared on the bottom. On the top, we have 1 plus t squared. Right? Times. Then 1 plus x to the power alpha. X to the power alpha becomes 1 over t to the power alpha. Again, common denominator, t to the power alpha. Then we have t to the power of alpha. And 1 plus t to the power of alpha. Right? It's I2. T minus 2. Here we can see that on the top we have t to the power of minus 2. On the bottom we have 1 over t to the power of 2. But that's still t to the power of minus 2. So they can just cancel out. Right? So gone, gone. So what do we have left? So it looks like I2 is now simply I have, on the top, I have t to the power of alpha dt. On the bottom, I have this part, 1 plus t squared times 1 plus t to the alpha. Right? So, here, change the boundaries and get rid of the minus sign. So it's from 0 up to 1. 0 up to 1. 0 up to 1. So it looks like it's very close to our first integral, I1. That's from 0 to 1 of this part, right? Except we have t to the power alpha instead of 1 on the top. Right? But in this case, we can still change. We will change t into x, right? From 0 to 1. just x to the power of alpha dx 1 plus x to the power of 2 times 1 plus x to the power of alpha, right? As long as we have the consistent variable, then it's fine. Right, so here we have I1 plus I2. What do they equal to? So now I1 plus I2. Again, I1 plus I2, right? Now we have the same boundaries. Right, from 0 to 1. We just need to add up the integrands, right? So this integrand plus this integrand, we have the same denominator. That's 1 plus x squared times 1 plus x to the power of alpha. On the top, we have 1 plus x to the power of alpha. Right? Then dx. And 1 plus x to the power of alpha, 1 plus x to the power of alpha, they just cancel out. Right? So in the end, our desired integral, right? Desired integral I is really equal to this integral already. So our desired integral is from 0 to 1, just dx 1 plus x squared. All right, that is very, very simple. That is equal to arc tangent x from 0 to 1. All right. 0 to 1. Like I said, t here, t does not equal to 0, but t could approach 0. Right? So later I've changed t into x. So in other words, in this case, x does not equal to 0, right? But x could approach 0, but it doesn't matter. So arctangent 1 is pi over 4, right? Arctangent 0, approach 0 is approach 0. So that's pi over 4. So in the end, we have pi over 4. Right? So it doesn't matter what the value of alpha is. It's always pi over 4. Right? If we want to be more rigorous, we can say, okay, maybe we can construct a function g of x that is equal to when x is not equal to 0, when x is equal to 0. So in the case of non-zero, we have the function we can construct, because just look at the integrand 1 over 1 plus x squared. All right? Then we can just say 1 over 1 plus x squared when x is not equal to 0. But when x is equal to 0, we already see that the function approaches 1. Right? So we can just say, okay, let's just define it to be 1 when x is equal to 0. So in that case, my constructed function is now continuous everywhere, including 0. Right? Then maybe we can just say, okay, we want to integrate from 0 to 1, gx dx, just to be more rigorous. Right? In that case, the function is really continuous everywhere, including 0, right, in that case. So in the end, it's just, so remember, the integral does not, so by changing the functional value at just one point, does not impact the value of integral. As long as the function integrand is bounded near that point, then we are fine. Just to be more rigorous. So now I'm done with the first method. So the second method, of course, a natural thought is to use the trigonometric substitution, right? Every time we see 1 plus x squared, then we immediately react to it, say, let x equal to tangent t, or tangent u, or whatever, tangent theta, anything. So we can let x equal to tangent t. So I want to know what's dx. right? So 1 over cosine squared t dt. That is 1 is sine square over cosine square, right? We can split the fraction. We have 1 plus tangent square. Right. Dt. Right, so in that case, what is my original integral? And remember, also change the boundaries. When x is equal to 0, what does t equal to? Here, of course, I require cosine t does not equal to 0. In other words, I require t does not equal to half pi. But t could approach half pi, right? Likewise. So when x is equal to 0, t is equal to 0. Right? When x is approaching positive infinity, t is approaching half pi. Right? So dx 1 over cosine dx becomes this part, 1 plus tangent square t dt. Right, what's on the bottom? 1 plus x squared. 1 plus x squared. 1 plus x squared. 1 plus tangent square. One plus x to the power alpha. 1 plus tangent to the alpha of t. All right, then we can just cancel out 1 plus t, or 1 plus tangent square. We're only left with this part. Right? So I is equal to 0 to half pi. Just dt 1 plus tangent to the alpha of t. Right? So what tangent t? So again, now we're going to use our lemma. Right? So this is easily verifiable. I've already proven that in a previous video. In fact, we can, just let a plus b minus x equal to t. A plus b minus x equal to t. Then in that case, dx is equal to minus dt. Right, also, remember, change the boundaries, right? So my right-hand side, this time is equal to, originally from a to b. When x is equal to a, what does t equal to? T equal to b. When x is equal to b, t is equal to a. Right, minus dt, minus dt. dt f of a plus b minus f of t. Right, f of t dt. Minus, we get rid of the minus sign, change the boundaries, right? From a to b, in fact. Ft dt, we change t into x as long as it's consistent. Right? F of x dx. Right? Again, my right-hand side is really equal to the left-hand side. So this has no problem. So now we can just easily look at our desired integral. So we can just let t equal half pi minus t. T becomes half pi minus t. Again, from 0 to half pi. dt. 1 plus tangent half pi minus t to the power alpha. Tangent half pi minus t, that is cotangent t. Cotangent t is 1 over tangent t. So in the end, we have 1 over 1 over 1 plus 1 tangent to the alpha t. Common denominator, tangent to alpha. 1 plus tangent alpha. Then I is really equal to 0 to half pi. That's tangent to the alpha t. 1 plus tangent to the alpha t dt. So the original I is this one. is also equal to that one. So I plus I, right, that's 2I is equal to same boundaries. A common denominator, same thing, 1 plus tangent alpha t. 1 plus tangent to the alpha t dt, right? So 2I is equal to integral from 0 to half pi, just dt. Of course, we require t does not equal to half pi, but t could approach half pi. So there's no problem with that. So 2I is equal to, in fact, just half pi. So I is equal to pi over 4, right? Like I said, just by changing the value of one point of this function does not impact the integral. Likewise, we can construct a function h of x that is equal to, when t is not equal to half pi, right? When t is equal to half pi. Now let's look at the integrand that is just 1. Right, so when t is not equal to half pi, my function is just constant, just 1. When t is equal to half pi, because I already know that as t approaches half pi, the function approaches 1. And so we can just let function to be exactly 1 when t is equal to half pi. Right? Originally, there was no definition at point half pi. Now we construct a function where it has definition everywhere, right? From 0 to half pi, including the edge of half pi. So in that case, continuous everywhere over this closed interval. Therefore, to integrate our desired integral is the same as to integrate h of x. The same thing. So nothing changes. Still pi over 4, just to be more rigorous.